after the class. So we start our last day with the last class of Glaucia's course. Enjoy. There's no announcement. Okay. So, hello everyone again. Thanks for being here after the very nice and tiring boat trip, and I heard there was a party again. Not joined, but it's very nice to see lots of you here. And so today is the last day that we will conclude this discussion on security proofs of QKD. So just to remind you again, here is our QKD protocol that we've been talking about all these days. So we had all the steps of distribution, sifting, estimating the parameters of the states that are being used for the QKD, and then all this classical post-processing. And what we talked about yesterday, we saw how we start from this last step, and we start getting information about how we model the channel, how we model all these actions that are happening to these strings of classical bits until we got to finally to the secret key. So yesterday we talked about steps 5 and 4. And with that, we determined that, I can talk about the key rate in the finite size regime, but maybe as a figure of merit for us to understand the most conceptual things, we can look at the asymptotic key rate, which was related to these two simple entropies. So it's the condition of von Neumann entropy of the bits that Alice generates after the measurement, and then either we have to bound it or to compute it with respect to the information that the eavesdrop has, or with the information that Bob has. Oops, wait a moment. Good. Yes. And I mean, this is the asymptotic key rate up to either like some constant factor that we lose because of the sifting, or also I'm not taking into account here the generation rate, so like how long does it take to generate a round. So let's just look at these quantities for now. And to remind that, so now we got to the point that we need to calculate something with respect to a quantum state. So what is this quantum state? So yesterday I said, so this is the state at the end of step 1. So after they finished all this quantum part, so there was a distribution, Alice and Bob made measurements, and then they ended up with some state which is classical with respect to Alice and Bob. So it's a CCQ state, so Alice and Bob are classical, but Eve has some condition information. So that's what I want to talk about today, so how we estimate this state. Good, so, and then from that we finally get to step 3 of the protocol, which was the parameter estimation. Maybe I can also ask if there was any question about yesterday or this recap so far. Good, if not. Good. Okay, so in the parameter estimation, at least for the BBA4 protocol, we are interested in our two parameters, the qubit in the X basis, which is the probability that Alice and Bob get different bits given the X basis, and also we also have the QZ given that they measured in the Z basis. So basically, since I'm only estimating these two parameters, I can rephrase my key rates now in the following way. right here. Okay, so what I mean by that, so initially here I just want to know which quantum state I have, and then I can calculate the entropy for this quantum state. But I do not know the quantum state. So in the QKD, I'm not doing the tomography of the state that Alice and Bob are sharing. We do not have the information about the state that the eavesdropper has, or at least we do not have access to it. So the only information that we have is this Q bears. So basically here I need to take the worst case scenario. So I will say whatever state that could lead to this Q bears, Qx and Qz, this could be the state that the source prepared, and this could be the information that the eavesdropper has. So we really need to take an infimum, to take the worst case scenario. And an infimum over what? So I'm representing all the states that belong to this set. So here we can say, let's say, a set of states that would lead to Q bears Qx and Qz. So the only thing I know, so here is BB84, so I'm measuring qubits. So I know I start with the qubit state, in the end I measure them. And I want to look over all possible states that if I would measure in the X basis, I would get Alice and Bob having different bits with probability that is given by the Qx that we observe in the quantity estimation. Okay, so now we see how step 3 again influences how we define our key rate. So finally now we can go to step 1 and try to model what is happening in step 1. Okay, so what happens in step 1? Initially, Alice and Bob, they would have an arbitrary quantum state, and I can put my eavesdropper here as well, and then they will make their measurements, and then they are going to end up with this CQ state. Okay, so basically our task is to say, okay, how can I look at all possible initial states that Alice and Bob and Eve could share, such that at the end I observe the parameters that I observe in the key distillation protocol. So here now my goal is to give a sketch about how we treat this, how we determine the states. Maybe sometimes stating some facts, not going to all the details, but I think this will give a good idea of how we really model this step 1 of the protocol. So the first thing I want to say, I want to state a fact that we can assume that my initial row AB is Bell diagonal. So let's call the Bell diagonal state rho tilde AB, and we can assume that because, so this is the fact, that if I have, if I look at the entropy of entropy with the eavesdropper of an arbitrary state, this is always bigger than the entropy with the corresponding Bell diagonal state. And I'm still going to talk about what is the Bell diagonal state, but just to justify why I can restrict to this assumption. And this is connected to Lina's question that, okay, why we are always going to the smaller than or equal. So to calculate my key, I'm going to use actually this approximation. So I might have another state, not a Bell diagonal state, but I'm on the safe side because I will in the end obtain a smaller key, and then it's secure for sure. Okay, so now what is a Bell diagonal state? So the Bell diagonal state is a state which is diagonal in the Bell base. Not much to that, but just to write it here explicitly, I will use this following notation. And these phi's, ij's are exactly the Bell states. And I don't know if you have ever seen in this notation, but it's a very compact way to represent the entire Bell basis at once. And so basically, I can represent all the Bell states by, I start with the maximally standard 0, 0 plus 1, 1 state, and then I can apply either X or Z, apply or not, and with that I obtain all the other states. So basically, in this notation, phi 0, 0 corresponds to the Bell state phi plus, phi 0, 1, I apply a Z, so I get the phase corresponds to the phi minus, phi 1, 0, I apply an X, so I get a bit flip, so this is the psi plus, and phi 1, 1 is the psi minus. So this is our Bell basis. So in general, an arbitrary 2-qubit state would have off-diagonal terms, but here we are saying let's look at this Bell diagonal state. And can anyone see what would be our Q bar in the Z basis if Alice and Bob at the end, so the channel distributed the state? So ideally it would be distributing just the state phi 0, 0, but either because we have an eavesdropper or because we have a depolarizing channel or the phasing channel, Alice and Bob end up with this other Bell diagonal state here. Okay, so they will not have the perfect state where they would have no Q bar, but they end up with this state. And it's possible to see from the state what would be the Q bar that they would obtain in the Z basis. So maybe here I should just say that all these lambda ij's are bigger than 0 and they are probabilities. So sum over ij is equal to 1. Any volunteers? Yes.
Will be lambda 0, 1 plus lambda 1, 1.
The 0, 1 is the phi minus.
But it will be a sum of...
Yeah, it will be some of them. Just so lambda 1, 1, definitely, because when I have lambda 1, 1, I have this state here, which is 0, 1 plus minus 1, 0. So every time Alice and Bob, they get uncorrelated states. So lambda 1, 1 is correct, it should be here. But just to set the lambda 0, 1 corresponds to this state here.
1, 0.
Yeah, exactly. And this state here has 0, 0 minus 1, 1, so they always get the same bit. So for these first two terms, Alice and Bob always get the same bit. But for the last ones, they always get different bits. So this exactly will correspond, so the probability that they have different bits will be this lambda 1, 1 and lambda 1, 0. So here now we see how our parameters that we are estimating during the parameter estimation, they are connected to the state that was distributed. And for the QX, then maybe it's not so straightforward. You would have to change the Bell base to see how the Bell states are written in the X base. Then I can just, so now it will appear my lambda 0, 1 plus lambda 1, 1. Okay, so now we even know like how these Q bars are connected to actually the states that I want to estimate. Now we need, so far I only talked about, I only talked about Alice and Bob, but now we need to put Eve. So we want to model the power of Eve. So to do that, I would like Eve to be correlated with Alice and Bob. I want to give Eve all possible correlation that she can have with this system. And somehow the Q bars are telling me, okay, you cannot have an arbitrary state, you need to have a state of this form because of our fact one. But if my Q bears are not 0, I'm sure that I have some components of phi 1 0 or phi 1 1. I don't only have only my maximally entangled state. So this is a mixed state, and it allows it to be correlated with another state. So then we will give all this correlation to Eve. So the way to model Eve is to give the purification of my rho tilde AB. Okay, so I'm going to say, okay, before the Alice and Bob started with the measurement, the state that was distributed that describes Alice, Bob, and now Eve is going to be the purification of my my bell diagonal state that I had here. So for this state, it's straightforward to write this purification. Where here I just have this Eij is a basis on each system. And I mean, the meaning of purification is simply that, okay, if I trace Eve for this big state here, psi ABE, I get back my original rho tilde AB. Okay? And purification is a nice way to model it, or even I could look at an extension, so I could look at other rho prime ABE, such that when I trace Eve, I again get my my original state. But the nice thing of the purification that any such state, any such extension of AB can be obtained by Eve doing operations on her purification. Yes?
I have a general question on modeling. So sometimes we also hear in language we say that the information of blah 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 is revealed, and then when
the information is what?
Is revealed. And does that is the modeling of it as this if you can model this the state that contains information with and then it somewhat is correlated with the outside environment or something like that. Because I don't know how this modeling is usually done.
Yes, in this case, I'm exactly modeling all the correlations, all the leakage that could have happened to my state. So, okay, I could think that actually let's do a parenthesis. The source actually produced the state phi plus, but then Eve tried to apply a quantum channel to this state before the state reached both. So Eve applied an ME to this, I will be imprecise in my notation, before it reached both. So the effect of this, so now if I trace Eve here, I actually get that Alice and Bob end up with this rho tilde AB instead of ending up with my phi plus here. So I could think of that. I only think in terms of Alice and Bob, and I optimize over all the maps that Eve could do. But then instead I can also say, okay, all these maps here are being modeled on the fact that I'm taking all possible extensions, all possible correlations that Eve could have with this final state here. So this somehow is modeling that all the leakage that happened because either because of noise, but here we are very paranoid, so I say if there is noise, it's actually Eve. It's being modeled by this, how Eve can be correlated with actually the final state that Alice and Bob obtained. If by chance my experiment is perfect and Alice and Bob have really this phi plus state, there is no way that Eve can get any information. So this channel would have to have been identity, and Eve is completely uncorrelated to that. Okay. Okay, so now we put the eavesdropper in here, and now we still didn't finish step one because they don't finish step one with the quantum state or AB, but they have to make a measurement, no? So now finally, at least for the key perspective, they will make a Z basis measurement. So that is the state that the basis measurement. that at the end I'm interested to calculate the entropy about this state. So in this case, we now have the state of Alice, Bob, and Eve, and then, Alice is going to make her measurement Z. Bob is also going to make his measurement Z, and now they will end up with a different state, which I can write in the following way. So with probability 1/4 when they measure that, actually you can see this because we are talking about this specific Bell diagonal state, and all the possible outcomes, 0, 0, 0, 1, which are not directly connected to these labels here, but all the outcomes happen with the same probability. You can simply, if you cannot see it directly, you can later do the calculation for this Bell diagonal state. So that is what I'm saying here, and then Eve will be left with a state which is depending on the outcome that Alice and Bob obtain. 0 plus 1/4 of 1, 1, 1. Wait, actually no, it's not the same coefficients. Let me call it C00. It's the same coefficients for the same probability, so here will be C00 as well, and C01 and C10. Now that's true, because depending if I have more, let's say lambda 00 and lambda 01 are bigger, actually there is a higher probability that they obtain the same outcome than that they obtain different outcomes. Sorry. Okay, so here I wrote in a generic way, so I wrote with these coefficients C00, C01, but of course these coefficients here will be related to the, so for example my C00 will actually be lambda 00 plus lambda 01 over 2. So they will be connected to the coefficients of the original state, and similarly the state of the eavesdropper is not so simple to express, but it will be totally connected to her basis states and all of these coefficients here. Okay, so that is just a cumbersome calculation to start with this purification here and apply the measurement and look at, okay, what are the C00s and what are the rho E00, but that is possible to do it directly. And at the end I will put some references. Again, I can refer to Renato Renner's PhD thesis where he goes through all these calculations quite in detail. Okay, so now finally this is our, so this is the rho CCQ state that appears on our calculation of our asymptotic key rate. Okay, so now again, so now I have a very specific state, of course, with lots of, with some free parameters. So it's not, the state is not completely determined, but it depends on these free parameters, but we know that some of these free parameters can be exactly determined once I know the value of my Q-bar. So it's a calculation that I don't have actually many free parameters in order to make our key rate minimization. And now I will just state the results. So if you go through all this calculation and now trace out Bob to calculate the entropy of Alice, even the eavesdropper for our CCQ state rho, you will get that actually you can write it very in a very simple form as an expression of the Q bar QX. Sorry, and here my H of a variable x is simply the binary entropy. So this is minus x log x minus 1 minus x log 1 minus x. So although again the calculation is very cumbersome, but in the end you end up with this very simple expression. And similarly for Alice and Bob, so I can simply trace Eve out of my CCQ state that I have here, which means that I will end up with a completely classical state from which I can calculate this conditional entropy. And this will be the binary entropy of my QZ. Okay. So that's to get to the point that in conclusion we get that the asymptotic key rate, and this expression, if you heard of the VIII protocol, you might actually have seen it before. It's 1 minus entropy of Qx minus entropy of Qz. Okay, any questions about that? Yes.
Hi, Glaucia. Maybe a silly question, but when you describe how Eve can intercept the state that is stored, I mean, I was wondering, and this is kind of overlap with Nadia's talk, if there is some non-Markovian noise, could it harness the backflow of information to get some extra information from this state, or? I mean, I don't know if it is arithmetic is busy.
So, I mean, Markovianity here maybe would be like when you are comparing rounds, no?
I don't know.
Potentially.
Yeah, when the channel is distributed, something.
Yeah, because, okay, I distributed one single copy, I will apply, so it's a bit like 1 times 10 in here, okay? But then the question is, I repeated 10 to the 6th time, so I have several time steps. So maybe here you can talk about some non-Markovianity, whether the action of the eavesdropper in step 2 depends on the action of in step 1. Okay. So yes, let's say non-Markovianity in this sense that Eve could apply a different strategy that depends on the previous strategy does give her more power. But then these theorems that I talked about yesterday, they are actually very important to show that, okay, this power, yes, we can handle it, and I can still recover this IID assumption, either because I have too many rounds of my protocol, or because I also have some randomness that even though the action of the eavesdropper might depend on the previous round, Alice and Bob can still choose the rounds independently.
Okay.
So there is some variables that are really non-Markovian here, and they are very important to make this possible.
Okay.
But it harms more, and that's why, but we don't see it in the asymptotic key rate, because very nicely all these results, they show that even this strongest type of attack, they are asymptotically equal to the IID one. But if you are in a finite size regime, you can really see how much you lose for, I didn't bring a figure about that, but you really lose orders of magnitudes of key because of considering coherent attacks, which here I would say that connect to this non-Markovianity.
Nice, very nice. Thank you, Glaucia.
Very nice, and also nice explanation. Follow-up question, do you know when the asymptotics kicks in, and if the rate is actually achievable? Like with rates, they are asymptotic, and it's not always clear that there's complete protocols to achieve them.
Okay.
And do we need 100,000 kicks or 10 billion?
A bit more. So, okay, actually, it's really a pity. So for the VIII protocol, that is one of the protocols we have the tightest type of analysis, because one can use the uncertainty relation instead of all this, just technical comment, instead of all this entropy accumulation theorem, so you don't lose on the square root of n terms because of your techniques. I think it's order of 10 to the 4, you start having key. So this is an important point. So here is the finite key, but if I'm talking about the rate of BB84, So this would be something like, okay, 1 minus qx minus h of qz, so I don't have my infinity here, minus some orders of 1 over square root of n now, because I divided by n. So this means that I need to have, I can, so at least for the protocols we know, you can see that the curves, they quite quickly, once you start having key, they quite quickly go to the asymptotics. So let's say, so my curve would be something like, so this is the key rate, and here is the number of rounds that I have. So because of this term here, if I have, I don't know, 10 to the 2 rounds, which is a lot, I have no key, because they are completely killed by that. So I start having key after some value of n, so let's say our n star, some n threshold, and then the key has to grow up to the maximum, so here is our asymptotic key rates that we are calculating. So typically when I see such graphs, maybe for sure like 2 orders of magnitude more than n star, you are already very close to the key rate. But okay, yes, fine. But for example, so if you're doing photonic experiments, which for the BBA4 protocol are okay, good. But if you are doing entanglement-based experiments, usually like you really need to generate 2 entangled photons. And for at least like experiments where they wanted to do the IQKD, some time ago was of the order of 1 event per minute. Maybe I can, well, let me quickly, I had some numbers on that once of the IQKD experiments that they made, but it's really like 1 event takes order of minutes or seconds. Yeah, okay, I will not find it now. So having to go 2 orders of magnitude more is too much, and having to have 10 to the 6, so this is for the BA4, it's order of 10 to the 4 rounds that you need. But more complicated protocols, it's order of 10 to the 6 or 10 to the 9, which is a lot of rounds that one needs. Okay. Yeah, so now I will finish soon with the BBA4 protocol because I want to comment a bit more on these imperfections. But now I would just like to mention, so if you exercise, if you calculate, okay, how much noise can I tolerate? So if my Qx is equal to Qz, okay, so I mean there is some value of Qx, so if Qx is 1/2, for example, so if I look at the binary entropy of 1/2, it's 1, so you can see that this term will already be 0, so my Qback cannot be too high, okay? So I would say the value here, but you can check afterwards. So let's say the threshold Q bears it's about 11%. Okay, so I mean this is quite good because experiments are now of the order of 2%. It's quite easy for the experiments for the BB84 protocol. So it's nice to see, and how this noise is connected to actually not having the eavesdropper, okay? So what could happen is that, okay, I have a source, I would like my source to be preparing the maximally entangled state, call it 5+, but then actually the channel is noisy, so there is a lot of noise on my channel, and what happens is that at the end I end up with something that, okay, I would like to have the 5+, but I don't have it, but otherwise my state is completely depolarized. So Alice and Bob basically share identity in this case. Again, we saw that the way we modeled it is that, okay, I'm not assuming that I have a depolarizing channel, I'm assuming that it has any information about this channel, okay? But actually in practice could be just that my experiment is not good enough, or all the experiments are never perfect, therefore I will end up with a state like that. Okay, and here you can see that how this thing is connected to the Q-bear. So does anyone want to guess what is the Q-bear? So in this case it will be Q-bear Qx is equal to Qz. and they are related to this depolarizing parameter P. So what would be this relation here? So with probability 1 minus P, I have phi plus, so I have no mistake, no? So I only, this is the problematic term that I have. No one? So the identity is like identity, so it's very mixed. So it doesn't mean that Alice and Bob will always get a mistake, but because sometimes identity is mixed, but it also is correlated. So sometimes they will get the same values, but for half of the times they will get 0, 1 or 1, 0 here. And half of the times they will get 0, 0 or 1. So actually this, so our QBAS are connected to this depolarizing parameter. So the QBAS is P over 2. So you can also see that, okay, if I have a depolarizing channel, I can, my P can be almost like 0.22, because when I divide by 2, I get to my limit of QBAS of having a positive P. So, I mean, VIII protocol is quite robust, so this is not something difficult. Maybe Steve can comment if it's difficult. I think it's not something very difficult to achieve such values of P and QBAS, no? So that's nice. Okay, so now any questions? Because now I want to talk a little bit about imperfections, but this concludes what I wanted to tell you about the security proof. Under all that assumptions that we discussed, that Alice either has a perfect single common source or we have entangled states that are distributed, and Bob is really performing X and Z measurements. And with that, we can guarantee that whenever I check my channel, I check the QBAS, I take the L, the size of the key, to be related to these quantities that we have here, that our key is secure. So, any questions left on this perfect VIII protocol? Okay. Wait, I need to change file. Yeah. Okay, so now I want to talk some more about some imperfections. So this will be quite informal, so I will not give as much details as before. Why can I not do it now? Okay. So, yeah, so if we remember, the first day we discussed a lot of assumptions. For example, that quantum theory holds, that the labs are isolated, that we have authenticated channels. So many of them I said, okay, I will not try to relax these assumptions, but there was 2 of them that was connected to the source needs to do what the protocol is telling it to do, and the measurement device needs to do what the protocol is telling them to do. So now I would like to discuss, because the source does not do what you would like it to do, neither the measurement device, so we would like to discuss how to relate that. And actually, it's nice, it's interesting, I'm not sure it's nice, but whenever you have an assumption and it's not satisfied, your protocol is completely subjected to be hacked. And there is many work, so as QKD is developing, so we have constantly like new protocols that are more practical, but we also have the research study of hacking QKD protocols. And this is also developing at the same speed. So as soon as someone comes up, okay, I have this protocol which is quite practical because I have a lot of key, then people will try to hack it, and well, usually not. The only way to hack the protocol is to detect that some of the assumptions were not satisfied and explore these assumptions. Because otherwise, we saw, like you used quantum information, quantum principles to do the security proof, so the only problem can be, okay, you can make a mistake on your security proof, of course, but usually if you didn't do that, the only problem can only be that some assumption that you made was not satisfied. So the first thing I would like to discuss is the BB84 with the imperfect source. So for this case, I'm interested on the prepare and measure protocol. So of course, if I have entanglement, great. I don't need to worry about the source, but entanglement is an expensive resource, and many of the protocols with high rates also expensive connected to the question of research, how many rounds we need. Many protocols, they...
Battery is coming. Oh, no, wait.
Maybe okay, let's see. My hands. Okay, so yeah, many protocols they actually do the prepare and measure version where we actually don't need the time. Oh my god, my voice sounds different. Okay, so actually, so one very common way, so ideally in our prepare and measure protocol, we would like to have Alice preparing one of these BB84 states. But this is, someone said first on the first day that one of the assumptions was single photon source, which we don't have a single photon source. So then people try to say, okay, let's have an almost single photon source. And the very common way to implement this is to encode, so my states, 0, 1, plus or minus, they are encoded in polarization. But not of a single photon, but an almost single photon. So people usually use phase randomized weak coherent pulses. So just to say a bit of the notation, so here we have a coherent state that has some intensity mu and some phase theta. And the idea is that you will take a state with a very small intensity, which means that at the end the probability that your state has only one photon or 0 photons is quite high, and the probability of having 2 or more photons is very low. So actually, I mean, this very complicated expression where you take a coherent state and you completely randomize the phase leads to a state of this form, where actually, basically, we can see this as, oops. So this Pn here is the probability that the source sends n photons. So because of this phase randomization, all the off-diagonal elements are killed, and basically we are left to some number multiplied by the number of photons. So the source is effectively distributing n photons with probability Pn. And okay, that's a nice explanation, but you can already see that I have an assumption here, right? Because, okay, I'm saying the phase has to be randomized, and this is also not difficult, and if the phase is randomized, I do not have this state, and potentially leakage for the eavesdropper. But okay, but maybe this is more realistic already than a single photon source, and people really try to randomize the phase properly. Okay, so once I have this state, good, but from our QKD protocol, we saw that only single photons events are secure. So okay, so the challenge here is somehow to estimate, okay, what are really the only single photon events? Because all of the others, they are insecure, so I should throw them away. But usually the photon detectors, they also don't tell you, okay, I detected 1 or 2 photons. There are photon detectors that do that. Yes?
Are zero photon events not secure? Are zero photon events not secure?
No, they are fine. Yes, they are secure as well. Because there is nothing for Eve. But they are also very random because there is nothing for Bob. So yes, they are secure, but they lead to Q bears because Bob will just either get a dark count or not. So they have to handle it. But Eve doesn't have anything. So yes, they are secure but bad. Are secure and good and useful, let's say. But yes. Okay, so the task here is then to estimate that. So in that respect, I will just now, wait. I'm just checking what did I write. Okay, good. So only for one photon events are secure. So let's see what happens. So now Alice is sending not a single photon, but her pulse. And it will go through the channel, and either Bob will have a detection or not. So here I'm saying, okay, I will say that this gamma is the probability that Bob has a detection. So maybe the channel completely lost the channels, the photons or not. And I can divide this probability that Bob gets a detection by summing over all possible events. So Bob gets a detection when the source sends 0 photons, then it will be the case of dark counts, or Bob gets a detection when Alice sent 1 photon, and so on. Okay, so here I'm just rewriting the probability that Bob gets the detection. Okay, so this, just to rewrite our entropy, so I actually want to calculate what is the entropy of Alice given E for our some state rho. And now I can break this entropy as a function of these different detection events. So here I did not consider the photon, the 0. I could also consider that I had the case, but maybe I can say that the probability that if I have no dark counts, probability that Bob has a detection when there was no photon, so this probability is going to be 0. So the stamp is not going to appear. But if you do have dark counts, you would take that into account. And how do I say, okay, so only single photon events are secure, so that is to say that, okay, maybe when I have 2 photons, Eve could have captured one of the photons, so she has full information about Alice. So again, we are being very paranoid, and I have to say that, okay, then this entropy here is 0. And the same for all other entropies connected to events where the source had more photons. Good. Okay, and then for the entropy of Alice and Bob, so how much information Alice needs to correct. Bob does not know if he received a photon, even if he had a photon resolution detector, it could be that he receives 2 photons, but actually the source sent 4 photons and Eve just captured 2. So Bob does not have information about how many photons were sent. So they have to correct for all possible events. So this will be related to the probabilities that Bob detects a photon times the entropy, the Q bars connected to the events that Bob observed. Okay, so now I basically, for treating this, let's say, the fact that whenever I have more than 1 photon, I have an insecure event, we can now modify the Q rate in the following way. So note that for the first term, I only have this quantity here that can contribute, so I will have a probability of this, 1 minus. And now it's the H of Alice and Bob, so this term remains the same, but note that here I have 2 different things. So here is the, well, as I said before, the probability that Bob detects and was a single photon event. And here is the Q bar connected to this event. So I'm so malicious that I'm assuming this is not the same Q bar that I observed, because maybe the Q bar connected to single photon events is different than the Q bar connected to 2 photons and so on. So this is the Q bar in X for single photon events. So good. Now in a clever way, I took care of this modern single photon events, and now I have a formula to calculate the Q rate. But the problem is that my gamma and my qz that appear on the formula, they are observed quantities. Okay, so qz is what Alice and Bob will estimate when they do the parameter estimation, and the gamma is Alice and Bob can check. Okay, Alice checks how often she sends some signal, and then Bob can say, okay, but from these I only got a detection 10% of the time. So they can simply check on the experiment what is this gamma and what is this qz. But the problem is that these other quantities, they are not observed. So I cannot directly get these quantities from my experiment. And this enters the technique that was the title of this session that I call the decoy states method. Good. Okay. So I will just state the idea of this method. So initially I said, okay, for getting to this key rate here, what we did was we said Alice, instead of preparing single photons, she prepared this phase randomized coherent pulse. And then this is a mixture of states with different photon numbers, where the probability of these photon numbers, you can see that it only depends on this intensity of these pulses. Okay, so the idea of the decoy state method is to, on top of doing QKD with these states, sometimes Alice is going to probe the channel, and to do that she's going to prepare phase randomized coherent with weak coherent pulses with different intensities. So that somehow, in a not so straightforward way, they can get more information about the channel, about what is the action of the eavesdropper for different for different events where the number of photons that was sent by the source was different. So just to state it, so these are lambda ones, and they can be lower bounded or upper bounded depending on what is necessary here. So they can be estimated using intensities. So these are what is called the decoy states to probe the channel. So to check how the channel acts on the photon losses, on how many photons I lose, but the channel again could either be noise that I have or could be the eavesdropper. So this method is like not very simple. So basically you can get, with this method you get an infinite number of equations, and your task is to see with the minimum resources, where maybe I use only 2 intensities, how can I nicely or give meaningful bounds for this? Again, we are going in the other direction of getting a smaller key than I could potentially get, but just to be on the safe side. And then people implement such first the theory using several decoy states, but experimentally using maybe 2 or 3 decoy states. But this already gives you it's very impressive, because I mean you get quite rough bounds on these quantities, but this is enough to ensure that you have a positive key. Good. So that's what I would like to say, like in overall and wavy way about the decoy states method, but just I hope it's clear that the goal here was to relax this assumption of coherent states and of single photon states, and of course you can find papers about hacking decoy states protocol because the phase was not randomized properly, and then people can explore this to obtain the key. Any questions? Yes.
So are security proofs always related to finding the secret key rate in terms of the Q bars in every protocol, or there are other ways to prove security of?
Yes, because the key rate is what you would like to, I mean, this is your figure of merit. You could, as well, instead of just looking at the Q-bar, try to make some state tomography, but this is just more expensive. And notice that, like, every parameter you are trying to estimate, you are going to estimate it in the finite regime, and you are going to have to take care of the variances in the non-IID setup. So this comes with more and more overhead. So this VIII protocol is very simple because it only requires to make measurements in 2 bases. And this is really the minimum necessary. You cannot do a protocol where you have only 1 basis, because then its classical information can be copied. But you could use the Y basis, and then you get higher key rates because you also estimate more things about your state. Okay, so you can do high dimensional systems where you even have more different types of Q-bars, and you are estimating all of them or only one. So the more you estimate, the better you get. But you also have to deal with the finite statistics. Okay. Good. So now I would like to talk a little bit about the technique of removing the assumptions about the measurement devices, which are usually also quite an important point about quite a sensitive let's say, part of the QKD protocol, because it can be very easily hacked. And the way it is typically hacked is just like you shine laser on your detector, and you blind the detector and you make it act differently. And this basically, it means that your detector is not anymore measuring X and Z, but it's just measuring whatever the laser you input in. So it's also a sensitive thing. And there was this proposal that was called measurement device independent, and we are going to measure device independent because we basically don't have to talk about the measurement device anymore. We don't need to trust it. It could even be in the middle with a third part, with the source and so on. So that's the idea of this measurement device independent, and it also has a benefit, a good thing, that we even get a longer distance. So I would like to now briefly talk about what's the idea here. So in the VIII protocol with entangled states, the idea we have Alice and Bob, we have the source in the middle that is distributing the state. Or we could have the source on Alice's lab and she's distributing. But now let's consider something different, just to see how it goes. So now Alice and Bob both are going to locally prepare a maximally entangled state. So they have A prime, B, and B prime, and they are going to send it. So this is time going. They are going to send it to the middle. Okay. So now their systems are here, and we have this measurement device, which hopefully is doing a Bell state measurement. So basically, this device is like projecting this state into a Bell state. So if you are familiar, or you can see, this is basically what's happening here is an entanglement swap. Because when A prime and B prime is projected on a Bell state, we have that A and B are also projected on the Bell state. So the entanglement was first between these two systems, and now we have entanglement between these two systems. So basically what this thing in the middle is doing is an entanglement swap. Okay, so depending on the outcome that I get here, which should be either 5+, my states are going to be, one of the Bell states will be left over for Alice and Bob. 20 minutes is well. Good. Okay, and then now Alice and Bob, they will do their measurement in the X and Z bases, right? And then, like, if they are doing these measurements, we have to look which Bell pair was projected. No? So if I have the 5+ and they are doing X and Z measurements, they should be completely correlated. If they get the 5- and they are doing X and Z measurements, they will always get uncorrelated outcomes. So Bob could just correct for that. Okay, but now, so yes, they do the measurements, but I could think, okay, everything here commutes, so they could do these measurements first. So Alice and Bob could do the measurement first, and later they would send their states A prime and B prime to the central station, okay? But sending these states, so now I can think of this, Alice and Bob already made their measurements, and now they are sending A prime and B prime to the central station. So when they measure their maximum, so this is basically, again, we are using this equivalence between the entanglement based and the prepare and measure scenario. So now Alice and Bob are preparing only these single qubit states, and the way they prepare it could have been that they had locally a maximally entangled state and they performed their measurement, or that they simply already prepared directly this single qubit state. And then they send it to the relay. Okay, so now I'm calling this thing in the middle a relay, which is supposed to do a Bell state measurement. And then this thing does a Bell state measurement and announces the outcome. And from the equivalence of this second one, where Alice and Bob are sending single qubit states from this scenario that we just discussed here, we have some relations depending on what the relay is saying. So if the relay says my outcome is 5 plus, and Alice and Bob prepared on the Z basis, they are sure, okay, our bits are equal. And the same for the X basis. If it was 5 minus, actually, if both prepared in the X basis, they know they have a bit flip, so Bob could simply flip his bit. Okay, so Alice and Bob, they know this information, but the relay does not know if they have the same, the relay can know that they have the same outcome or different outcome, but the relay doesn't know if it's 0, 0 or 1, 1, okay? So basically this was the way. So before, in the BBA4 protocol prepare and measure, Alice was sending the single qubit states to Bob, who was supposed to make a measurement. And now what we did for this MPI, we explored this entanglement-based version, sending this entanglement-based version to a central station that does an entanglement swap, and this is equivalent to just Alice and Bob sending this to the central station. So now we have prepare and measure, where the only thing that is measuring is this relay, this thing on the center, which is not Alice and Bob. Could be Eve even. I don't really have to trust it. And Alice and Bob now they only have to prepare states. Clear? This argument is a bit cumbersome, it takes some time to get used to it, but here is basically the equivalence of entanglement based with the prepare measure. So now you see that somehow we got double the distance, because before Alice had to send the state directly to Bob, and now she sends it to a central station, Bob does the same, and this central station has to do the measurement, which I don't have to trust anymore. So we got double distance and we got no assumptions about the measurements. Yeah, so maybe, so here if, so this relay is not trusted, and they just want to make these remarks. So we got a longer distance for free, let's say for resources that are not from Alice and Bob. So, I mean, that's very cool about this protocol. And on top of that, so now I have here that Alice and Bob should prepare the single qubit states, but we can still use this method that we discussed in the beginning. If Alice and Bob don't have single photon source, they can use decoy states to access how is the channel. So the decoy state method can be incorporated. So added here. So then it's very nice that we actually completely remove assumption about the measurements, and we even remove the need for single photon source. We can have these V coherent pulse phase randomized ones. So this protocol is very nice, and people, so here I discussed as if we are using polarization as a degree of freedom, but people also use like frequency or other degrees of freedom that gives even higher rates for the generation here. I will really not enter in details on that, but all of these protocols based on this idea that, okay, whatever system I'm using to mimic the BB84 states, if it's mimicking it well, I will get the security that I would like to have. Good. Questions? No. Now, my final thing, because I was not thinking, I was planning not to talk about that, but it's something that I really like, and Steven and Steve mentioned it on their talk, so I thought it would be nice to at least mention a little bit. So here, when I talked about, okay, we are relaxing the BB84 protocol, but we still need to model our system, either as a single photon or XZ measurements, or as weak coherent pulse. So you see that we are relaxing the assumption, but then we go into the experiment and we need to know more details about that. I need to have a phase randomized weak coherent pulse, which is a resource that I can have, but I really need to describe how the system is. But then, using these very strong correlations of quantum mechanics, we actually can completely remove the assumption. So I don't really need to know what my system is doing. And this would give us the possibility to completely drop these two assumptions that I was talking about, that is to know which state is being prepared and to know what state is being measured, what measurements are being performed. So this is the idea of device-independent QKD. So device-independent means it does not depend on the device that I have. So it gives us super strong security. But as you might imagine, of course, the key rates that we have now are not great, and the techniques that are necessary for proving security of this protocol are also much more complicated than for the BB84 protocol. But then just to give an idea what it means, so for the BB84 protocol, we had Alice had to prepare, Bob had to measure, and they were estimating this these two quantities QX and QZ. But then when we go for the IQKD protocol, the idea would be Alice is preparing something, sorry, not even Alice, I would have to really go for the entanglement-based version. The source prepared something, so some state which I don't know, and the measurement devices are making measurements which I don't really know. By don't really know, it means like, yes, in your lab you need to know what you are trying to do, but for the security proof, it doesn't matter if you try to implement a Z measurement and actually you are measuring a higher dimensional degree of freedom, or if you try to prepare the 5+ trait, but actually you prepared, I don't know, there is other degrees of freedom that you are controlling, or noise, or blinding the detectors. All this type of attacks would not work for the IQKD, because for the security proof, I'm not saying what is wrong, and I'm not saying what is in the measurement device. So the idea here is that, okay, in the BB84 protocol, Alice and Bob, they could measure X bases or Z bases. Here I'm going to say they are going to make two measurements, measurement 0 or measurement 1, but I will not really say what these measurements are. And then they get their outcomes, outcome 0 or outcome 1. So with that, they connect these probability distributions, and then okay, so that's what they are doing in the step 1 of the protocol. But now they get to the parameter estimation phase. Okay, so before I was measuring QX and QZ, and I mean even the names of my parameters has the label of the basis, so it's very device dependent. And here we would need to estimate a parameter that is device independent. So what is it that we are going to estimate in a device independent protocol? Steben really mentioned several times what we need here. A Bell test, yes, we need a Bell test, so we need to look at for a Bell inequality. So let's say we need violation. Of a Bell inequality. Which, for example, could be the CHSH inequality. So actually, Alice and Bob are going to look at, they will sacrifice some rounds, so this would be the parameter estimation. right? Just for completeness here, these correlators are related to the probability A equal B, given the measurement, which I don't know what they are, A different B given XY. So you see that, I mean, it's quite similar to what we did for the VIII protocol, that somehow we were estimating this was connected to the Q-bar. Now I'm estimating a bit more complicated function where I'm using all possible correlations that I obtain here, but I'm looking at the baryon equality. And then, okay, but how does it enter in QKD? And just to give an idea of the difficulty of the problem. So now in the parameter estimation, good, I estimated beta, the value of this expression. So now what I would have to do is the following. So I would have to look at all possible quantum states. Remember how we started the lecture today? We modeled the quantum states that Alice and Bob share, give the purification to the eavesdropper. So we would have to do this again for all possible quantum states. That gives violation beta, and then I calculate my entropies for this state. And I take the infimum because I need to take the worst case scenario, because we never know if this is actually the state that was implemented here. So again, so now before my set S was the set of states that would lead to QBAS, so now is a set of states that lead to violation beta. Okay, so great, very easy. I do the experiment, I get my Bell violation. What is the problem here that we would face? To do the same thing that we did for this lecture today, that I started with Bell diagonal states, and then I looked up, why can I not start with a Bell diagonal state here? And then look up, okay, what are the lambda 0, 0, lambda 1, 1 that gives me this Bell violation beta? No one?
You don't define the state that you agree.
I don't say.
Define the state you agree.
But in the BB-8 also I did not define, no? I said general state. But it's related to that. I'm not defining something that in the BB-8 I defined. Yeah, so the measurements of the BB-8, once I say it's X measurement and Z measurement, I'm somehow defining that I have a qubit. That's why I could already immediately go to qubit. But here I'm saying I have a violation beta. So the measurements here, they are binary, they have binary outcomes, but they could live in a higher dimensional space. So then, in the sense, I'm not defining the state, I'm not even defining the dimension of the state. So we can say here no assumptions on dimension or the measurement as well, because I don't say my measurement is in the X basis and then I could restrict to qubits. So I would just like to give a flavor. So the protocol, in principle, it has the same steps. No, we have distribution and measurement, we have sifting, we have parameter estimation, information reconciliation, private simplification. But then, following the same steps, I end up with this equation which looks exactly the same, but somehow fundamentally is much more complicated because I don't even know the dimension of my state. Almost finished. The dimension of my state. So, I mean, that's why when you see the IQKD protocols, you mostly see them with the CHSH inequality, where people really understood how to do these calculations, and it's extremely complicated to look at all the baryon inequalities for really doing the same analysis again. So, but on the other hand, we get this extremely strong security proof that we have no assumptions. Okay, so now, just before finishing, I would just like to show an example of one specific protocol that was implemented. Just maybe, is there any questions about the IQD? Because I will now finish with that. Yeah, good. Okay, so just before finishing, I would just like to show an example. So the BB84, so back to the BB84 protocol, it has been implemented a lot, and people are constantly advancing. You see on archive, today they implemented over 300 kilometers fiber with megahertz. So people are both trying to improve the distance and the rates that one can obtain by improving the generation rate. So I like this example because I think it's not the best ever implementation. So nowadays you find implementations with higher rates and higher distance. But I think it was very remarkable to show that we are achieving a nice level, and they made such a paper maybe really to advertise QKD. So this was a PRL, and it was a collaboration between researchers in Austria and in China. And they even encoded, so okay, we can go to the abstract, that they encoded a video conference that was performed between Austria and China using QKD. And to do that, so you can see that we see all the words that we learned in the course, no? So they perform a decoy state quantum key distribution protocol. In this case, they used satellite to work. So yesterday there was a question about the architecture. So here the satellite was a trusted node. I will show a picture later. So, but they were implementing exactly this protocol that we discussed today about the decoy states. So they create a key over like an extremely large distance, and you can see that they generate kilohertz of key rates every time the satellite passes on a specific point. So this is the figure that they have in their paper. So here we can see that the network was actually, so there was first a QKD generated between this point in Austria and then that point in China, the one over there, and then another key was broadcast here. So the endpoints were actually these and these for the video call, but they had two extra nodes in the network, that was this point on Earth and the satellite. So connected to the question of yesterday, in this case, these extra points, they all were like trusted repeaters. So the satellite would do BB84 key here, and then later satellites keep moving on Earth, do BB84 over there, and then broadcast the same key, and then they even use the fiber. And again, just to illustrate the points here, they have the Q bands that they obtained for different days. So you can see they were all the order of 2%. The sifted key, which now you know what it means, it's after they remove all these rounds where they measure in different bases. And then the final key that they obtained, that then after information reconciliation and privacy amplification, that was of the order of kilobytes. So I think this nicely illustrates, and many of these protocols which are really used nowadays are really connected to the BB84 protocol, and thanks to all these security proofs that we could see. Okay, then maybe with that I will end. So just some suggestions if you want to read more about QKD. So there is the PhD thesis of Renato Renner that I mentioned. So it does not contain the latest techniques, but like all the latest techniques were based on that, and it's very didactic. Then there was this paper, and it has a very, how can I say, a name that they really wanted to do a largely self-contained and complete security proof of QKD, and I have to say they do that. So they also discuss many problems in security proofs. They use a specific technique, but it's very nice as well. And now QKD is even starting to have books. So Ramona Wolf, recently she published this book where she even has some exercises in there. And I already heard of more books coming up. So QKD is even get to the level now of the textbooks with the nice advanced security proofs. And with that, I thank you, and I'm happy to answer questions today as well afterwards, or you had my email on the first lecture, feel free to reach out. Any questions? Any questions?
So there, like most of QTD implementations actually use VIII, right? There are some relevant examples that use other types of protocols that like work.
I was going to say yes, they have time being frequency encoding, and this has some problem of security, but actually they are trying to mimic the VIII states as well. So nowadays, there is continuous variable QPD. So that's maybe another one that is implemented where we really model like infinite dimensional states. And other than that, there is theoretical claims that if we explore higher dimensions, we really get an advantage, because if I have a system of dimension 4, I have 2 bits making a single measurement. So intuitively we expect that, but this even like the noise models for getting advantage are a bit controversial, so you don't see much implementation on that. So when you really, there is proof of principles, yes, or the IQKD, for example, that was last year. So proof of principles are really happening, but for practical protocols, it's usually VIII is the best we have.
What about Eckert 91? There is a VIII-like.
So the Eckert would be exactly this DI that I talked about. Indeed, maybe I. So the one, the original idea appears in this paper of Eckert, but then it was only in 2016 that we really had a security proof for the IQKD. And indeed, they are using the one that uses CHS inequality is exactly the Eckert protocol. So yes. And you see that it was, Eckert 91, so it was proposed in 91, but it took even more than 20 years for us to get security proofs for that. And implementation only last year.
In the device-independent version, the expression for the key rate simplified if you consider self-test instead of any bare inequality.
So if you consider self-test, the problem of self-test is that you have self-test only when you have maximum variation. So yes, you could have maximum variation and then you can just compute this entropy, assuming that you have the self-tested state. And then you can see that here you already get maximum entropy because Eve is not correlated with Alice, and you just look for Alice and Bob. But we have this problem of self-testing results do not translate in a nice way for the noise. So you see that BBH4, I have epsilon security, epsilon 10 to the minus 10, and the noise is 11%. While in self-testing, if you go in this way, the epsilon you would get in a, let's say, straightforward way, it would be exactly of the order of the noise you are tolerating. So we need, it might be an idea, but we don't know how to use self-test robustly.
Okay, so so if hypothetically someone had access to beyond quantum resources like a PR box, where would this security break?
Already in the first step that we had, we don't have a private amplification against non-signaling advanced rate, for example.
But even if it's still a non-signaling resource, beyond quantum but still non-signaling.
Yeah, no, but exactly. So if I assume, so we don't have a theorem for a good theorem. I think there is one result that they show you can get 1 bit of key. I'm not absolutely sure, but we definitely don't have the same level of, I assume the adversary is non-signaling, but I need to do private simplification. And that is the result that we still don't have. So it starts from the very beginning that I don't have this private simplification. On top of defining entropies that make sense for GPTs in general, that would be another problem, but even the private simplification results.
Thanks. Okay, with that we thank Glaucia again. Glaucia, thank you very much for the nice course, for accepting our invitation, and we retribute with some cachaça.
And please, let's have 20 minutes of coffee break. because after the second lecture, the second course, we will still have some things to do, including taking the official picture of the event. So 20 minutes of break and we resume at 10 past 11.
Okay. Surpresinha mais tarde.
That's a good question. I guess what I Thank you.